So this is part 2 of the moderators modules, and we did in part 1 the categorical moderator, and now we're going to do the continuous moderator. So continuous moderators, we're going to use weighted regression in order to fit the model. I assume that you have some experience with regression for primary studies, and the most common variety is the OLS, or ordinary least squares regression. And what you do is you estimate a line for some data points, and you assume that there are equal error variances for the values of y at each level of x. This is the homoscedasticity assumption. You estimate the magnitude of error and you minimize the sum of squared errors you place the line in such a way that you minimize the sum of squared errors. So that's your ordinary least squares regression. With weighted regression, the error variances are assumed to be known but unequal. So we don't know what they are in OLS, but we assume that we do know what they are in weighted regression, and they're not the same across the various observations. So what this means is in meta-analysis, we have these effect sizes, and we know the sampling error variance for each of these effect sizes, so we can use weighted regression with these sampling error variances. And now we're going to minimize the weighted sum of squared errors. I've got the two columns here, one for OLS and one for WLS. And if you are at all familiar with the matrix representation of OLS, it's the B weights are x prime x inverse times x prime y. And the variance of error we find by the sum of squared residuals. So each observation is y and predicted value is y hat. So we subtract the predicted value from the actual value, square that squared difference is a squared error. We divide by the degrees of freedom to get a mean squared error, or the average squared error. P is the number of predictors, N is the number of observations. The variance of the B weights is x prime e inverse x to inverse of the whole thing, and the diagonal elements of that are labeled C sub jj, so 1, 1, 2, 2, 3, 3, the diagonal elements. The traditional test of the regression weights is the B weight, which were estimated up at the top, divided by these diagonal estimates, which are the standard errors, and that's the thing that you get in the x prime e inverse x whole thing inverse. So that's a typical test for a slope for B, is that t value. All right, with weighted regression on the right column, we've got V is equal to a diagonal matrix that has on the main diagonal the error variances. Whereas, those things would be the same in OLS. They're different as we go across the matrix in weighted least squares. So if you look at the regression weights B star, you notice it's the same thing except that we've inserted this V inverse matrix. So we're going to have inverse variance weights here, just like we did have inverse variance weights in finding the mean in the Hedges tradition. So here we've got the estimates of B star, and here we've got the variance of B star, and now we've substituted for that error matrix. We've got this matrix V, which has got the errors in it. And so we also have the main diagonal, and then we pick the JJ element for that. Then we take the square root of that. That is our standard error. So the diagonal elements are the variances of the regression weights, sampling error variances of our regression weights. So here we have T is B star sub J over square root of C sub JJ. So the difference is we're just using these inverse variance weights in calculating the regression weights and their standard errors. All right, so here's a hypothetical example. We've got correlations that go from 40 to 65 here. We've got the Z transforms of those correlations. We've got the sample size for each of these studies. The weights are n minus 3, as is conventional. Now, what we're looking at is the correlation between people's SAT quant scores and their GPA across their freshman year. But we're looking at the percentage of quantitative courses they're taking in their freshman year. So you can see in the first study, we've got 200 people in the study. The correlation between GPA and SAT, GPA and SAT quant is 0.4, and 10% of this group's classes were quantitative. And down at the bottom, we have a correlation of 0.65, and 30% of their classes were quantitative. So what we're going to try and see is, is there an association between the observed effect size and the percentage of classes that are quantitative. Okay, and so in the upper right, you see the formula, that matrix equation for solving for the regression weights. It's x prime v inverse x, quantity inverse, x prime v inverse y. And so I've got the matrix X there. It's got ones in the left column and the percentage of quant in the right column. And the ones are for finding the intercept, and the values of quantitative percentage are for finding the slope. Y is the outcome. That's our values, R to Z transformation. These are, and then in V, we've got off-diagonal elements are 0. We've got a diagonal matrix that has little numbers like 0.05, 0.06, so those are 1 over n minus 3, the error variances. And x prime, you can see, is we just flopped it over on its side. The V inverse, you can see, is that matrix V, and now it's the weights in it, so it's 1 over the variances here. So this is going to be, the inverse variance weighting, just as we did for the garden variety meta-analysis. So to find the regression weights, we solve that x prime v inverse x to quantity inverse and x prime v inverse y, and we get 0.27 for the intercept and 1.67 for the slope when we do that. When we find this variance matrix, variance of B star, we've got 0.62 and 154 in the main diagonals, and we've got, for the off diagonal, we've got minus 0.289. So a little matrix multiplication, get these. And now, there's got to be a point to doing this, right? The variance of B, those are our sampling variance. So when we take the square root of those, we've got the standard errors. And so we've got a standard error for the intercept, and we've got a standard error for the slope, and we've got an intercept and a slope. So the t-values, we're going to divide our estimates by their standard errors, and that will give us a value of t. So 0.27 divided by 0.0787 is 3.41, so that's our value of t for intercept. And then we've got slope of 1.67. We're going to divide that by 0.3924, and we get 4.25 t-value for the slope. Okay, so we were estimating our slope and intercept. That is our line that relates the percentage of SAT quant to the freshman GPA, and it's the regression equation is 0.27 plus 1.67 times percentage of quant, and we can see that we've got values of t that look pretty good for a significance test. Okay, so so that's a sort of a fixed effects analysis. In the event that the homogeneity reveals there's still a large Q value for the residual, we can use that Q to estimate the residual random effects variance. And then we can use that to recalculate weights for specific values. Usually we don't do that, but There it is. Okay, so the weighted regression in R, we're going to use the metaphor to do this meta regression. Okay, so here's the input. I showed you the Z and W, and V is 1 over W, and here's the percent quant as I showed you earlier. And what we would do to get metaphor to calculate this for us, we would say RMA for the R meta-analysis, that's the metaphor command, y sub I is equal to Z, V sub I is V, mods. So now notice there's no factor or anything here. I just say it's distributed as percent quant. So this is a quantitative variable, and it's going to treat it as such. Method is DL data data 2. So I've asked it for this for the random effects variance component estimate. It says it's a mixed effects model with 6 studies. Tau squared estimator is Dersimonian and Laird. It says its estimated residual variance is 0, and tau is 0, and I squared is 0. So it looks like the moderator accounts for all of the random effects variance in this. Residual heterogeneity says it's not significant. Test of moderators. Okay, so this is the coefficient here. It's got 1 degree of freedom. We got a Q value of 18.9, P value of 0. So this is the test of the moderator. That's what we want to know. Okay, so here's our intercept. This point is 26, and 1.70 is our slope. Okay, and we get tests. It says both of these are significantly different from 0. My results are a little slightly different, but that's because of rounding error for Z. Okay, example 2, relations between LMX, so that's a leader-member exchange theory, and other variables. So we're going to look at people's, these are survey results, where we've got people rating their leadership and then how much they are committed to their organization. So people with crappy leaders tend to quit. That's the basic idea. So they're looking at the correlation between people's ratings of their leader and their own affective commitment to the company, and they're looking at country classification. So these are studies that have been done in different countries. So are they Western, are they Eastern culture by the Hofstede collectivism scale? And so that's one moderator. The second moderator is going to be the reliability of measurement of the affective commitment in the sample. So the idea is that the higher the reliability, the larger the effect size should be. So now, in the Schmidt and Hunter approach, you would just disattenuate the correlations by that reliability. You wouldn't include that as a moderator. But in the Hedges approach, the reliability of measurement is considered a moderator, just like any other moderator. Okay, so I've read in the data, and here it says RMA, so we're going to run metaphor. Y is Z, variance is V. Mods are distributed as, here's the factor, and this is the cultural, the collectivist versus individualist. And here's alpha, which is the estimate of reliability for that study. And we're going to use DL for the random effects, and here's the name of the data. So now this is like analysis of covariance, right? We've got a categorical predictor, and we've got a continuous predictor at the same time. So it says, okay, we found, we're going to run the study. We've got 92 studies in here. Tau square, here's the estimate of the residual heterogeneity. So I didn't show you this. I could run this without the mods, in which case it would give me an initial estimate of heterogeneity, but this is what you get after you control for these two things. Here's tau, I square, still 78%. Test for the residual is significant, says there's lots of random error. And now notice that the test of the moderators is 2 and 3. So 1 is the intercept, 2 or 3 are this one, and this one. So it's the cultural and it's the reliability. And that's not significant, so it's like your overall R-square is not significant. So you should probably not be going beyond this, but because we're doing, and you probably just stop here, but because we're doing this as an instructional video and what it means, then I'm going to go through and interpret all this stuff. So intercept is 0.2353, and the confidence interval includes 0. Now here we've got the culture, and that's not significant, and here we've got the reliability, and that is not significant. So we got a whole bunch of nothing here. It says there's lots of random variance, but it's still a pretty good size. So the studies are wandering around a bit, but the moderators that we have don't seem to be explaining that variability. Well, we could go back and say, I told you in the previous video that most of the time people don't run models with more than one independent variable because of missing data. Oftentimes the different studies are missing different pieces, so when you put several moderators into a regression you get all missing, and so there's almost no studies left. But in this case that we actually do have plenty of studies. But what will happen if we just ran one of these? Well, we got 92 studies, and we're just going to look at alpha. So we're just going to look at reliability. And here we got the residual left is 145, tau 78, it's pretty much like it was. Test for residual, it's still pretty big. Test for the moderator, it's not significant. It is not significant. So we don't get an effect for alpha. Well, what else? Well, what if we forget alpha and put in just the collectivism, individualism? Well, we still got 92 studies. We got pretty much the same tau squared. We got a lot of residual heterogeneity. We've got no significant Q for our cultural variable here. And when we look down at the estimate, this is interesting. So now this is significant, but this is not. So there's no effect for culture by itself. Okay, so here's an exercise for you to try to do the same thing, only do it for job satisfaction instead of affective commitment. Try that.